very happy to introduce Jeremy Hahn, who's going to tell us about exotic spheres from p-adic cohomology theories.
Right. So yeah, as the last speaker of the workshop, I think we all owe a huge round of applause to Kustus, Barrow, and Jacob and the IS. Well, thank you for organizing this, and personal thank you for inviting me to speak and to participate in this special year in general. And so what I want to talk about is sort of an application of a lot of different mathematics, but in particular of prismatic cohomology to a question in differential topology. And so in a moment, I'm going to jump into some differential topology, but you might ask, why am I doing this at a, where's the prismatic cohomology going to enter? So maybe I'll just say a few sort of vague motivational remarks that I don't want to get horribly hung up on yet, but maybe we'll circle back around to in the back half of the talk. So we've heard a lot about these functors constructed by Bhatt, Levy, and Drinfeld. And so they gave these wonderful functors, which take a sort of p-complete ring and output some algebraic stacks. You could take the prismatization of slope of that ring, the Nygaard stack, or the homotopy. These are some stacks. And the coherent cohomology evaluated from these stacks computes e.g. The symptomic cohomology of R, or the prismatic cohomology, depending on which stack you use, with coefficients. Coefficients being given by some kind of sheaf or perfect complex on these stacks. And this is the input to a variety of spectral sequences, the symptomic cohomology. It's a wonderful cohomology theory. And from an algebraic topology point of view, I'm particularly interested in the use of symptomic cohomology as the input to computations in algebraic K theory. You may, for example, have heard of work of Antio, Nicholas, and Krause that give new computations of the algebraic K theory of some very basic rings using symptomic cohomology and this formalism. But there's an observation, maybe some work in progress. Sana Devalapurkar in the audience, and myself and Raksit and Arpan Raksit and everyone who are during this special year, which is that the functor are, say, going to our prism or our Nygaard or sin, they naturally are defined not only on p-complete rings, but on a whole subcategory of p-complete ring spectra. Whatever it means. So these ring spectra were the subject of a lot of Jared's talk. So these ring objects in the category of spectra. And this can be used to make computations the K theory of ring spectra, and not just of the algebraic K theory of rings. And that sort of is a beautiful subject because it has an arithmetic flavor. These stacks, when we plug in rings, have some sort of flavor of arithmetic geometry, But the output, when you evaluate this K-theory on ring spectra, can sometimes be related to problems in geometry or differential topology or things like this. And so just to give you an example, before I get into the differential topology, I could look at the prismatization of the p-complete sphere, right? So this thing is the moduli of formal groups with the section. That's just a teaser. So this is the same object S that Jared wrote. I think a lot of homotopy theorists tend to write a blackboard bold S, just as one writes a blackboard bold Z, you know, for the initial ring. And so this is the prismatization of the initial ring, and it's giving you this moduli of formal groups with the section. There's a map from the initial ring to the integers, so you get a map from Z prism to S prism, and that classifies this Drinfeld formal group. Okay, anyway, let me not dwell on that.
Sorry, I have a live question. So,
Yeah.
so previously you say that it defined on p-complete rings on without any condition or have something like Gaussian LCI or whatever.
Well, I think now there's something maybe for any animated ring, but
No, but the problem is that forgettable factor from animated ring to infinite ring is not fully feasible. I mean,
yeah. So
so I wonder in what sense your later construction is an extension of the previous construction.
I think there are various things one can do, but there is a sort of quasi-symptomic category where this is easiest to define, as you're sort of pointing to.
I think someone, question, what's a section of the formal group?
So the moduli have formal groups, has living over it the universal formal group. And I think this is that. But I really would like to talk about differential topology a little bit. We'll come back to this at the end. So thank you. Okay, so let n be larger than 4. I want to talk about sort of n-dimensional things in large dimensions. I don't know very much about 4-manifold theory or anything like that. So let's get a definition. Homotopy n-sphere smooth oriented and manifold and homeomorphic to the standard n-sphere. So this is something that's sometimes called an exotic sphere, but I could also have the standard sphere as my homotopy n-sphere. You might wonder whether all homotopy n-spheres are just the standard sphere, but Milner famously proved that there are counterexamples to that in dimension 7. And in fact, due to work of Milner, Snail, one can organize this set of homotopy n-spheres say considered up to orientation preserving diffeomorphism. Into a finite abelian group. There are finitely many homotopy n-spheres up to diffeomorphism, and they form an abelian group, theta n, with group operation given by connected sum. So if I'm given two homotopy spheres, I can cut a little disk out of each of them, glue together the punctured homotopy n-spheres, and get another one. So I want to ask sort of the following basic question. Prime, does the p rank or the dimension of f be tensored with this finite abelian group grow as n grows. And you might wonder sort of how many exotic spheres are there? That would be some question about the cardinality of theta n. And I want to ask some question like how many exotic spheres are there that genuinely are not related to each other via connected sum type operations? So some questions about the rank of this group.
So I wonder, here you take smooth guys. Is there any difference if you take other variants like PL versions or topological versions? I mean, in their definition of homology.
Well, some of this is handled by some versions of the Poincare conjecture due to Smale, and I don't want. We'll soon discover what I want to talk about. I was a little worried that, I'm going to try to talk about a lot of different subjects, and I'm more or less expert in various parts of this story, but let me see. So I want to answer this question about smooth structures. Right, and so in particular, here's a theorem. Write it over here. The main theorem of the talk. We're really to now I'm going to write some names here of my co-authors, but of course there's a lot of reductions going back decades that go into this, which is that the limit as capital N approaches infinity of the sum of these dimensions and so on average, these p ranks are growing. The average p rank is tending towards infinity as the dimension is tending towards infinity. Yeah, and this is the kind of thing that I think was largely inaccessible until very recently. And sort of, if you want a statement like this, you kind of need to use a lot of different areas of math, including some of this symptomic cohomology stuff. Okay, I want to sort of explain a couple of reductions of this theorem that sort of move farther and farther away from smooth manifold theory and closer to number theory. So the first reduction is going to be to homotopy theory. So something about continuous geometry rather than smooth geometry. Okay, and so homotopy theory, we're going to study something like a pointed topological space, not necessarily with any kind of smooth structure or anything like that. And we're going to be interested in these homotopy groups, I n of x, which is of course the set of continuous maps, continuous pointed maps. From Sn to x up to continuous deformations known as homotopy. And so this is an abelian group as long as n is larger than 2. The group structure given by the so-called pinch map is a map from, say, a two-dimensional sphere where I just pinch the equator to a single point. So I get these sort of two bubbles. Now, if I have two maps from two different spheres into X, I could use one of them to define a map on the top here, one of them to define a map on the bottom, and then composition through this pinch map gives me a group structure. And so one might wonder about these abelian groups, but in general they're a little chaotic. There is a nice theorem for this all. It says that for k sufficiently large, I n plus k of Sk is independent of K. And this group is called the nth stable group, and the difference in dimensions of the sphere is exactly n. And in other language, it's pi n of the sphere spectrum that Jared talked about, if you prefer. Okay, and maybe I can just remark that there's some theorem of Cartier-Milnor. There's an exact sequence. It's an exact sequence, Pm plus 1, beta n, and stable group mod some subgroup J, Pn, and here Pn and Pn plus 1 are cyclic. And J is a cyclic subgroup of this nth stable group. And so what that means is that the P ranks, the dimensions of FP tensor this group and FP tensor pi n stable differ by at most 3. So if I want to understand the asymptotics of beta n, I may as well study the asymptotics of stable group, the nth group of the sphere spectrum divided by n. And that, so these are the same theorem, essentially, once one has this Cartier-Milnor theorem. And we've seen our first big reduction. We've gone from smooth manifold theory to something about the homotopy groups of the sphere spectrum, a continuous problem. And maybe this is some indication, that these spectra and these stable homotopy groups, as opposed to the general homotopy groups, are more often connected to other areas of mathematics, or arise often in other contexts, like in differential topology. Okay. I mean, some of these might be, this is a finite cyclic group, and these have finite image, at least. So they're the image of they're finitely generated.
I mean, pi n stable is just finite, right? So
Oh, well, yeah, for
n positive. So.
yeah. Right. I mean, sorry. So let me say what this is. Yeah. So these can be Z's or Z mod 2s and things like this. So, as you may have guessed by this being the homotopy theory day, what I actually want to study is the growth rate of these stable homotopy groups of spheres. Okay, so I want to make a remark about this stable homotopy thing. X is any point of space one writes reduced stable homotopy of X. The limit as k goes to infinity, I n plus k of k-fold suspension of X. This is some kind of dimension shifting operation. And so this is some generalization of the Drinfeld theorem that I mentioned, that this stable group exists, and it's telling something about the homotopy groups of some shifts of x into larger and larger dimension. And then if x is unpointed, write I unstable of x, which is in this reduced thing where x with a disjoint base point. So you just add a disjoint base point and take this limiting thing. So this is a homology theory. So the transformation of the functor x goes to I star stable of x is a homology theory. As Jared mentioned, all spectra are essentially the same thing as homology theories. So this is this homology theory called the sphere spectrum. It measures stable homotopy groups. And it's the homology theory, again, it's called the sphere. And I want to just point out that it is a homology theory in the sense that you can use Meyer-Vietoris, you can use excision, you can use various familiar operations to understand the stable homotopy of the space in terms of the stable homotopy of some kind of decomposition of that space. The only thing that is a little bit awkward is that if you do that procedure, you're eventually going to want to know the stable homotopy of a point. But the stable homotopy of a point is exactly a collection of these groups that we're trying to study, in which we will probably never completely understand. Nonetheless, this is a homology theory, and so we can talk about stable homotopy groups where any space X, and I want to just set up this theorem, which is suppose X is any finite CW complex such that the homology, reduced homology of X, FP coefficients, is not entirely zero in all degrees, then I can say that the limit is n approaches infinity of this dimension homotopy of X. This is plus infinity. Okay. And so really, I don't know, I want to mention this for general X because in some ways you could move away from, you could phrase some of what will come later, especially for large primes without using symptomic cohomology, but especially if you want this kind of result at small primes or you want it for general X, I think this p-adic stuff really, really essentially enters the story. Okay.
Do you have any corresponding result for p power n torsion as well?
Well, maybe not at the moment. Okay, yeah, so for the remainder of the talk, very end, I'm going to focus on primes greater than or equal to 7. There are certain statements that just become a little bit cleaner to say at large primes, though none of the results are essentially relying on this assumption. I want to say something not about all the stable homotopy groups of X. I'm really interested in the ones that are p-power torsion, and I kind of want to just treat all p-power torsion equally, at least for the purpose of this result. I'm interested in the rank. So there's a sort of way of saying that very cleanly, which is to study a related but slightly different homology theory. There's another homology theory, or spectrum, if you like, which is called the mod P stable homotopy. it's evaluated on the space. And it's defined to sit in an exact sequence. Stable homotopy of X. Any abelian group has a multiplication by P map. And the colon of this will be the P stable homotopy. And then that goes to I star minus 1. I star minus 1 via the multiplication by P map again. So this is the unique homology theory, which fits in a natural long exact sequence like this. And so it's the mod P reduction of stable homotopy. You might call it S mod P. Okay. Now there's an absolutely wonderful, beautiful, not totally transparent construction maybe atoms and tota, so that there's a natural transformation V1, which goes from the mod P stable homotopy of a space to the mod P stable homotopy of that same space, but it shifts degree. It shifts degree by twice the prime minus 2. Some bizarre natural transformation, degree shifting natural transformation from this homology theory evaluated on X to itself, but with a degree shift. And this makes this homology theory graded FP adjoint V1 module. Right, so if I consider all the degrees at once, the direct sum of all these degrees, then I have this FP module structure because I mod it out by P. And I have this V1 operation, which I can view as making the whole thing into a graded FP adjoint V1 module. And the study of chromatic homotopy theory really begins with attempting to understand this homology theory in these groups using this extra structure of this V1 multiplication map. So what we want to understand, if we want to understand exotic spheres, is the mod P stable homotopy of a point. And there's a theorem about that due to James Miller. It says that if I take this mod P stable homotopy of a point, which we want to show is going to grow quickly, and I invert V1, well, then I'm going to get some FP adjoint V1 plus minus module. That's a field. So what I'm going to get is a two-dimensional FP adjoint V1 plus minus vector space. So we said that we're never going to understand the stable homotopy of a point. We're never going to understand the mod P stable homotopy of a point explicitly. But after we invert V1, this is just a two-dimensional vector space. So this theorem
As a graded ring.
as a graded ring, every module is free.
Okay.
Right. So so you know it's a two-dimensional free module, but that comes for free. Okay. And so you know what we're trying to prove is that there's a lot of stuff in this group before inverting V1. And what this theorem says is that almost all of that stuff is going to be V1 power torsion. If you're looking for a large collection of elements, you're never going to find it after inverting V1. It's all V1 power torsion. And in fact, what Miller proved was something much more general than this. What is this theory I'm describing? It's exactly V1 S mod P. Right? That's what it is, a spectrum. Spectra are homology theories. And he proved that this is V1 S K1. Where this is the object that appeared in Jared's talk. So I won't need to use this language, but if you know, now that we've seen this beautiful talk defining these kinds of objects, this is the real theorem here. And it makes it like really possible to compute with this homology theory in general, using this kind of Galois descent.
Is it possible to say something about the generators?
Yeah, I mean, you can name them before inverting V1 and you can see what they are in the stable stems. And I don't know, be happy to talk more about that. Okay, so this is this nice theorem of Miller that relates this sort of theory that's kind of directly built out of the sphere. We don't have to do any kind of localizations or anything with this kind of theory that's local. Okay. But I don't want, to study small answers. I really want to produce a lot of elements in the stable homotopy groups of spheres. And we just said that they're all going to be V1 power torsion. So there's a sort of next step. We can think about another homology theory. And look at I star stable mod V1, some spectrum, some homology theory of spaces. And it's designed to sort of understand V1 power torsion. And it sits in an exact sequence. It's characterized by the following exact sequence. I could take mod P, stable homotopy of X, is this V1 transformation, which increases degree. And then I'm going to have mod P V1 theory. And then I'm going to have mod P theory again. This one, and then mod P theory again. 3, 2P minus 3. It's exactly the analog of killing P. We're killing now this transformation V1 to produce a new homology theory. And now, beautiful construction. There's a natural transformation. V2. Goes from the mod V1, stable homotopy of any space, to mod V1, but with a degree shift of 2p squared minus 2. Okay, and so what does this do? This makes the mod P1 stable homotopy of X. And at the adjoint V2 module, where now V2 shifts degrees by 2p squared minus 2. You might notice that V2 shifted things by 2p squared minus 2, V1 by 2p minus 2. V0 is what sometimes people call P, and that shifts degree by 2p to the 0 minus 2. So there's this sequence that we can use to really study stable homotopy theory, and that's very related to this tower that Jared was talking about that reassembles the sphere from its KM localizations. Okay.
Could you make a remark analogous to the remark you made on the work you just covered?
So let me say something. So there's a conjecture. I'd rather know. Late 70s, the so-called telescope conjecture. And the conjecture says something about what I get if I take this mod PV1 and invert V2. And so what Ravenel thought, at least in the 70s, is that this is a 12-dimensional FP adjoined V2 plus minus vector space. So that's the conjecture. This is some specific 12-dimensional thing. And remark is that Ravenel actually conjectured, if you like this language of spectra, that if I take V2 invert, S mod PV1, this is the same as V2 invert V2 local sphere mod PV1. These are the same homology theories. And if that conjecture is true, which looks very plausible given this Miller result, it would imply that you could study this theory using that map from SK2 to E2 that Jared talked about in the law descent. Right? This conjecture gives you a strong tool for computing this homology theory. And in particular, using that tool, one can compute that the answer for a point should be this 12-dimensional theory. Okay, but the theorem y is that V2 inverse pi stable PV1 point is infinite dimensional. So it's not 12-dimensional in particular. And so therefore this conjecture is false. Okay, so this kind of formally implies all this stuff about smooth structures. You go trace back through the exact sequences, completely elementary arguments will then tell you that the number of smooth structures on a sphere grows quickly with the dimension, or grows with the dimension on average. So this is the main result, this infinite dimensionality. So what's the sort of rough strategy that we're going to use to prove this thing is infinite dimensional? Let's study the unit map. From the sphere to an algebraic K theory of some ring spectrum that I'll call Jm. And here Jm fixed points and then Adams operations I am acting on swing K. So this is some object in homotopy theory, some ring spectrum. It's actually something we've already encountered in Jared's talk. So if you look at this E1, this Morava E theory at height 1, that's got in action by this group called G1. And this is the fixed points of E1 by some element in that group. There's different elements you can choose in that group, and that's why this M I'm leaving as a variable. And so we want to understand something about this unit map. And we're going to study what happens to this unit map when I mod out by P and V1 and invert V2. Okay. So the main point is that there's a theorem of Burklund, myself, Levy, and Schlank, which we explicitly compute the homotopy groups of this spectrum V2 inverted K Jm for some values of M, for some of these elements of this group, some Adams operations. So we can just completely compute this thing. We can name every element in it. We can understand it very well. It's wildly infinite. Okay, but that's good. We want to see lots of things. I think I should point out that taking the fixed points of an operation is like taking the fixed points of a Z action. And there's sort of beautiful theorems of Akil Matthew here maybe, and collaborators that say that this kind of infiniteness can only occur when you take the fixed points by an infinite group, like the integers, and not by a finite group. Okay, so we want to study this unit map.
Did you say what K was?
That's algebraic K theory.
Does K theory apply to
This ring spectrum. So I said, algebraic K theory, like symptomic cohomology or prismatic cohomology or any of these other theories, we can study them on ring spectra and not just on rings.
And Jm was the fixed points of an Adams operation acting on
On height 1E theory, KU.
KU meaning E of 1.
Yes. Means topological K theory if you're like actual vector bundles or something.
Your definition of JM has no dependence on M.
Well, there's this psi M here that may be difficult to see.
Oh,
Certain Adams operation acting. Okay, so we explicitly compute this. It's wildly infinite. And then something I'm not going to talk about is some work of, some work involving some of the other names that appeared in the previous theorems. We use ambidexterity, whatever that is, that Jacob had a hand in, to produce lots of elements in the homotopy groups of this guy. So we can produce lots of elements using some machine called ambidexterity. And we just need to show they're all linearly independent. Like you might worry that they all will be 0 or something. In fact, that's the hard part, is to check that they're not all just 0. And we check that by mapping them here and observing that they're linearly independent in this thing that we can completely compute. Okay. So I think maybe sort of the key thing to explain, at least from the point of view of where p-adic geometry enters, is how can we compute this? Why is this so much more computable than the V2 inverted S mod PV1? And it's a consequence of the following sort of key result. I take the algebraic K theory, this JM guy, and I mod out by P, V1, and V2, kill V2. And this is concentrated in degrees -2 less than or equal to star less than or equal to 2p squared plus 2p minus 2. So almost all of these groups, almost all of the homotopy groups of this thing are 0. There's a finite number of values of star for which these are non-zero. They're going to be very infinite for those values. But it's bounded. There's finitely many degrees that are getting involved. And this, if you just think about the exact sequence that relates working mod V2 with not working mod V2, with very little additional work, implies that if I take the Tate theory of this AM guy, mod out by P and V1, this is a 3. Be a joint V2 module. This is bounded range of degrees, and the definition of the long exact sequence that relates these things makes it extremely difficult for this to be anything but a free module. And so if it's a free module, then I know what happens when I invert V2. So not only do we calculate the V2 inverted thing, we calculate the thing before inverting V2, which is mod PV1. But somehow the reason we're able to compute any of this is because we do almost everything mod V2. So this is this kind of very powerful but strange maneuver. If I want to understand what happens when I invert V2, well, I'm going to study what happens when I mod out by V2, and somehow that's formally going to tell me what happens when I invert V2. Maybe a little bit surprising. So I want to compare this to a fact that might look a little bit less exotic. So I don't know, let A be a sort of local number field, and P. So something, not, let's leave the world of ring spectra and think about things that are closer to this conference. I could study the letter that you want to use. Okay, let me just say, is that okay? Yeah. So if I look at this ring of integers, I can compute the algebraic K theory of that ring, and I can mod out by P and V1. And
You're still in the local case, right?
Yeah, everything is local. I'm imagining something like ZP.
Say number field there.
I had a conversation earlier with Jared in which I said Z for ZP, and it was highly offensive.
I think if you just cross out the word number, everyone will be happy.
Yes. Yeah. But I can compute the algebraic K theory of this thing, and I can mod out by PV1.
But you exclude the equal characteristic. It's a static field or
it's ZP, okay? I don't know.
Wait, is the P the same as the denominator?
Yes, the P is the same as the denominator, and this is, so this is supposed to be I'm committing the dangerous act of moving into the realm of expertise of the audience. Okay. Can mod out by P and V1, and this is concentrated in finitely many degrees. So it's the same phenomenon, exactly. When you mod out by enough of these VIs, all of a sudden this thing has finitely many degrees of interest. This is Thomason's reformulation of the so-called Lichtenbaum-Quillen conjecture. For K or something, or maybe K. And so, you know, this Lichtenbaum-Quillen conjecture was proved in great generality by Blatsky. But I just like, this is, you know, this is a statement that has some history to it, right? This Lichtenbaum-Quillen conjecture is exactly, by Thomason's reformulation, the statement that this is concentrated in finitely many degrees. And so now, I mean, you know, nowadays, if you wanted to prove something like this, you could actually do it pretty easily. And Lu Wang proved this by just computing the cohomology of this symptomification in twists of the structure sheet mod T of V1. V1 is this element that you invert to get a tall cohomology.
So is there additional input because K is not literally like TC, right?
Yeah, but you know, so you want to prove something's in a finite range of degrees. There's a spectral sequence starting with symptomic cohomology. TC, yeah. So there's some trace methods, and the relationship between symptomic cohomology and K theory is something that's nowadays well understood, but it requires some serious theorems to set up. But essentially, given some theorems, this computation is more than enough to imply this. And this computation is explicit. They just go and compute.
Purity or something.
Well, I don't need to.
It doesn't matter.
So one consequence of this computation is that if I don't mod out by V1, I'm going to get a free FP adjoined V1 module. It's the same phenomenon going over there. When you mod out by V1, you don't have much stuff. That means that you're kind of a free module. And that sometimes, I don't know, that's one thing people call purity sometimes.
Statement that this is now easy, is that specific to the case where, okay, the p-adic field?
Absolutely. As an example, any prime p, I don't know, I sort of at some point restricted to primes larger than or equal to 7. Let me ignore that for a moment now. If I take the cohomology of Ku P spin coefficients in the structure sheet, let's see, this can be explicitly computed. In fact, it was explicitly computed by myself, upon Raksit, and Dylan Wilson. And it's, you know, something vaguely along the lines of this Lu Wang thing. You just sit down and compute, and that implies that the algebraic K theory of this Ku satisfies a Lichtenbaum not mean much beyond the fact that if you mod out by some powers of P of V1 and V2, that this is bounded in the range of degrees. By the way, I've been writing lowercase Ku I mean, Jared was talking about E1, that's kind of like a field. This lowercase is for the ring of integers in the field. So you should think of this like the ring of integers in this thing Jared is calling E1. Okay. Right. So, one thing I wanted to say is just that atomic cohomology is one tool for proving Lichtenbaum-Quillen style theorems. Here, the key thing powering this proof of the telescope conjecture is a Lichtenbaum-Quillen type thing, but not for KU, but for some fixed points. So the main result in this paper is a way of understanding how to deduce Lichtenbaum-Quillen type things on a fixed point if you know it for a ring. So we know it for KU by some explicit computations, generalizing some computations of algebraic K theory that were very influential by Assini and Rognus. And then once we know what happens with KU, this work tells us that there's something that happens with these fixed points also. I think it's kind of open, how often this kind of thing happens. What's the greatest generality or the correct level of generality in which one should expect these kind of Lichtenbaum-Quillen things, these bounded algebraic K theory statements after you mod out by some collection of VI. So I would think that's a very interesting question. Every time we prove these statements, they can even have consequences for differential topology and things like this. That's pretty much all I wanted to say, but maybe let me close by remarking that we would like to know more. About the geometry of KU-P-sin. These wonderful theorems about the geometry of Z-P-sin. And even though this is defined using some kind of ring spectra nonsense, KU is not a classical algebra object, this symptomification is just a classical stack, something which is very familiar to the realm of algebraic geometry. So this is some stack that some machine turns homotopy theory into a classical algebra geometric object. I'd like to say something about it. Here's an example of a kind of thing you can observe, which maybe indicates that something interesting is happening. So I could take the symptomic cohomology of perfect complex, and I could mod out by p-v1, and I could map that to the same thing with v2 inverted. And this produces, this is some work in progress for some of us here, produces a Lagrangian refinement of duality. This is a sort of nice theorem that was really explained well by Bargov in his notes, his theorem of Bargov and Jacob, that there's a similar Lagrangian refinement of the duality on the codomain. If you took, the Bhatt-Leary theorem is about taking ZP-sin, modding out by P and inverting V1. And in this context, you would mod out by P V1 and invert by V2, and some very similar sort of things seem to happen. So anyway, maybe I'll stop there.
Yeah, thank you very much. Questions?
So you mentioned that you use p-adic theoretic to use explicit computations, but it sounded like maybe you didn't need that to show the infinitude statement that you needed for the main theorem.
So I think the idea is that we somehow do this with this JM thing is explicit, and it comes from the fact that this is explicit. And we need some way of proving, we need some pretty explicit control of at least this thing to get off the ground to proving the main theorem, I think.
I mean, can you have something like, I mean, do you know what Ravenel was getting at then? I mean, can you make a better conjecture? Sort of, this is completely off base.
Well, you can, so there's this map from the cohomology theory we were studying to the K2 local version. And you can ask, sort of, you know, how many theories are there in between? There's a, say yes, but I think, I mean, it's a lot of open questions now because prior to this, they could have been the same. So measuring the difference is now, I think, a very significant question.
Question?
I hope,
So you go, sorry.
How does one define a KUP sinks? KUP is a ring spectrum.
Yeah, so this is, you know, talk to me after. I'm very happy to talk about this, but I didn't get into it at all. Yeah.
So the duality on the target that this is a refinement of, is that something recognizable?
Well, I don't know. So it's some kind of thing that is of the flavor of Tate duality, but also maybe of the flavor of the fact that the stabilizer group is a Poincare duality group. So I don't know that I like this is kind of, I don't understand the full picture of what you're supposed to do here.
can I ask one, regarding these like stack things? So I mean, syndrome application is like a very complicated kind of thing, and I was surprised that you get like actual stacks here. But there are simpler sort of stacky constructions like the kind of maybe even a characteristic 0. I guess you can probably still do that. Do they give you anything like that I would understand?
Yeah, I think there's some conjectures about that, maybe preliminary. I mean, I think, you know, obviously one would want to study like the Hodge-Tate stack first. It's going to be simpler.
So it looks like you're looking at only maybe a small part of the homotopy groups of spheres to get this asymptotic result. Only at height 2. If you were to look at more, is there a conjecture about what you might be able to put in the denominator in this asymptotic result?
And I think, you know, it's kind of wide open questions.
So these stacks, they're classical stacks, right?
Yeah.
But then, so these elements V1 and V2, they now come as, I don't know, global sections of the structure sheaf?
Yeah. Yeah.
Is there, so what's the, can you write more precise relation? Like whether there is a map from, I don't know, multiple groups of some?
You know, I mean, I think, so maybe there's a sort of TC definition of symptomic cohomologies, that it's the associated graded of a filtration on TC. And that maybe expresses this as related to homotopy groups of the associated graded of spectrum. I mean, there's something going on that's a little bit not spectral because we've landed in pure algebras.
Yes, okay.
So this V1 is defined on ZP thing, right?
Yeah, when you mod out by some power of P, some power of V1 becomes kind of well defined.
And is V2 also defined on ZP?
Yeah, well, so yes, but it'll be like 0 or something silly.
Wait, so in this proof strategy, in the step 1, like, is there some, like, what was the motivation for using this target to detect these elements?
So there are 4 of us, we all had different motivations. My motivation was that we had been proving some Quillen-Lichtenbaum things, and I wanted to prove Quillen-Lichtenbaum for this, and you go start computing and you realize the telescope conjecture is going, I mean, like, this Quillen-Lichtenbaum conjecture statement is very powerful for computing V2 inverted stuff, because somehow you get it for free when you work mod V2. And I think the main obstruction to the telescope conjecture being disproved is just computing the V2 inverted homology of like anything interesting. So this is something where you can do it because of this Lichten-Willenbohm thing.
Is it, sorry, go ahead.
Okay, this is probably gonna be the last question because the dining hall is gonna be very unhappy.
Is it possible to get something better than the n in the denominator and the main result?
Yeah, there's some things you can say and maybe some work in progress, and I'm happy to talk.
All right, thank you, Joe.